Good morning to all. Myself Dr. K. Manoharan, Associate Professor, Department of Biomedical Engineering. So today class we are going to discuss about the Butterworth Low Pass Filter design problems. So take the problem. So the given problem is for the given specification design an analog Butterworth filter for the range of frequency. So the 0.9 less than equal to h of e power j omega and then less than equal to 1 for the range of frequency 0 less than equal to omega less than equal to 0.2 pi. That means the attenuation is lies between the value 0.9 to 1 for the range of frequency 0 to 0.2 pi. And that value h of e power j omega will be less than equal to 0.2 for the range of frequencies 0.4 pi to pi. That is, the range of frequency above this 0.45, the attenuation must be less than the 0.2. So this is the given specification. So from this first we need to write the given values and we can draw the graph. Look at this graph. So they mention it as 0.9 to 1 for the range of frequencies 0 to 0.25. Look at this. I am taking this is a 0 and this is 0.25. So from this frequency range from 0 to 0.25, they mention it as the attenuation is 0.9 to 1. So I am taking this is a 1 and this is a 0.9. So from 0.9 to 1 only this is the value will be lies. Look at this. So from this 0 to 0.2 the value is lies from 1.0 to 0.9. So this value always greater than 0.9 and it up to value will be 1.0 for the range of frequencies 0 to 0.25. So we have meted this first constraint. Now look at this second constraint. So this value, that is attenuation, is less than 0.2 for the range of frequency 0.45 to pi. I am taking this value. So this is 0.45. So and this is pi. So from 0.45 to above the values. So from 0.45 to pi, the values below 0.2. Look at this. This is 0.2. Look at the graph. So below this 0.2 only available throughout the range of frequencies. So from 0.45 to till pi, the values lies below the 0.2. Look at this. So this is the below 0.2. Now we have matched the second constraint also. So this is omega pi, this is 0.25 and this is omega s, this is 0.45. Here alpha p alpha is not given. So instead of that we can use this value to find the n value. Look at this, they given us omega p is 0.25 and then omega is equal to 0.45. And then look at this value, I am mapping this value, so this is 0.9. So we map this value as, we know that this is 1 divided by root of 1 plus epsilon square. So I am taking this 1 divided by root of 1 plus epsilon square will be equal to this 0.9. Similarly, I know this value, this is 0.2 here. So 1 divided by root of 1 plus lambda square, that will be equal to 0.2. Look at this, 1 divided by root of 1 plus lambda square, that will be equal to 0.2. So by using these two expression, I can find the epsilon and lambda. By using that, I can find the n value. So if you resolve it, so here look at this, this is the 1 divided by root of 1 plus epsilon square will be equal to 0.9. Now we can square on both sides. What happens? 1 divided by root of 1 plus epsilon square will be equal to 0.9 square. Again, so we have cross multiply this. So 1 equal to 0.9 square into 1 plus epsilon square. So once if you multiply inside this, so we keep epsilon square one side and remaining all another side. From this we can find an epsilon square. Taking a square root on both sides, we can find an epsilon. So normal formula is, so we know this n greater than equal to log of lambda by epsilon divided by log of omega s by omega p. Instead of alpha p alpha s, I am using this formula because we have this lambda and epsilon only. So by solving this, we can find an epsilon. So this will be equal to 0.484. And solving this expression, I can find an lambda. So this is equal to 4.898. Now we can substitute this epsilon value and lambda value, and from that we can find the n value. So n greater than equal to 3.434. Now rounded to next higher integer. So n becomes 4. So n equal to 4, we need to find a h of s. So we know the tabulation for each n value, we know the denominator functions. We can refer it. Look at this. So this is the n value and this is the denominator function. Now refer this for n equal to 4. So this is the transfer function. So s square plus 0.76537s plus 1 and then s square plus 1.8477s plus 1. This is the denominator of h of s. So if you write a h of s, 1 divided by this denominator function gives an value of h of s. Look at this. I am writing here h of s equal to 1 divided by the denominator function. So s square plus 0.76357s plus 1 into s square plus 1.8477s plus 1. So this is the denominator function for n equal to 4 from the tabulation. So I am writing this is the h of s. Now I need to find a omega c. So omega c equal to omega t p divided by 10 power 0.1 alpha p minus 1 divided by 2n. So we don't have this alpha p. Instead of that I can use this as an epsilon power 1. So this 10 power 0.1 alpha p minus 1 power 1 by 2. So this becomes epsilon. So if you replace this, so epsilon power 1 by n only becomes. So omega p divided by epsilon 1 by n. So if you substitute here, so 0.2 pi, this is omega p and epsilon value is 0.484. So 0.484 power 1 by n, so 1 by 4. So this is equal to 0.24 pi. Now we substitute these values in the expression h of s. So s should be replaced by s by omega c, s by 0.24 pi in h of s. So h of s we have this s square. So s square is replaced by s divided by 0.24 pi square plus, so here also we have this s. So 0.7637 into s divided by 0.24 pi. So this s is replaced. Plus 1 we can keep it. So here also we have the s square. So s divided by 0.24 pi whole square and then this 1.8477 we keep it the value and then into s. So s divided by 0.24 pi plus 1. Now we can simplifying this, we get the expression 0.323 divided by s square plus 0.577s plus 0.576 pi square into s square plus 1.3793s plus 0.0576 pi square. Thank you.